We've established that the concept of impulse is very versatile in solving problems, but it's also versatile in explaining everyday observations. The two observations that we talked about yesterday that impulse can explain are when we have what I call a predetermined impulse, and when we have what I call that fancy two-hyphen word, non-predetermined impulse. What's the difference? I'm not asking you to explain anything here. I'm just asking you what I mean by a predetermined impulse versus a non-predetermined impulse. What's happening when you have a predetermined impulse? Yeah, good. The object is stopping. Now, when an object is stopping, we know what its impulse will be based on the initial conditions of that object. An object is moving down a path, down a road, down a sidewalk, through the air, if it's an airplane. If we know its mass and we know its velocity and we know that object is going to come to a stop, we know what its impulse will be no matter what. It doesn't matter whether it comes to a quick crashing stop or whether it comes to a slow gradual stop. That airplane that you're traveling in that weighs several tons and is moving at about 900 kilometers per hour, one thing is certain, it will stop. We don't know how it will stop. We hope it will stop the way that it's supposed to on the runway, but it will stop. The impulse experienced by that airplane is determined by how fast that airplane is moving and how heavy the airplane is. It doesn't matter how it stops, the impulse will be the same. So when you're stopping an object, the impulse is predetermined. It's going to be the same no matter how it stops. Now, when we have a non-predetermined impulse, we don't have an object that's stopping. We have an object that is starting. Now, it's not necessarily starting from rest. We gave you an example yesterday of a golf ball that's sitting on a tee that, of course, is starting at rest. But the same thing would apply to a baseball that's being pitched towards you. You swing the bat and hit the ball. You're starting an object, or you're starting it moving in the opposite direction, or you're starting it moving faster, or something like that. Typically, in that situation, you want to impart as much impulse as possible. So the impulse is not predetermined. It's dependent upon who hits it. It's dependent upon how hard you hit it, all kinds of different factors, okay? As opposed to when you're stopping an object, doesn't matter what happens, the impulse is going to be the same. All right. So we know what situations it explains, but how does it explain it? The basic equation that applies in both situations is delta P is equal to F times T. That's part of the impulse equation, right? M times delta V is equal to F times delta T. In the first situation, impulse delta P is going to be the same no matter what. So let's say that impulse is 100. If that impulse is 100, and let's say the time that it takes to stop the object is 20 seconds, what's the force going to be? If the time is 20, the impulse is 100, the force is going to be 5, right? 5 newtons. 5 times 20 is 100. What if the impulse is 100, but the time is increased dramatically to, let's say, instead of 20 seconds, it's going to be 50 seconds. So we're increasing the time that it takes to stop the object by a factor of 2.5. What's that going to do to the force? Well, what times 50 is equal to 100? 2. So you can see that by increasing the time of contact, the force acting on the object decreased. Now, it goes the other way as well, right? If for whatever reason you wanted to increase the force, which usually you don't want to do, but if you did, then you could decrease the time of contact on purpose to accomplish that. This is, as we said yesterday, the basic, one of two basic principles behind every single thing that cushions an impact, from you jumping off of a desk and bending your knees, to somebody who's a goalie wearing goalie pads, protecting themselves from a puck, to an airbag in your car protecting your head from hitting a steering wheel. The idea is increase stopping time, decrease force. It's almost certain that you'll get a question on your diploma exam that asks you this question. I don't know what the context will be. It may be the context of an airbag, it may be the goalie pad, it may be jumping off your desk, or it may be some other context that we haven't thought of. But it's likely that you'll get a question that asks you about cushioning. Okay? The answer is, no matter what the context of that question, the answer is impulse stays the same, increase stopping time, decrease force. So whatever the question, that's the answer to the question. Now, when we have a non-predetermined impulse, we're starting an object, sometimes from rest, sometimes not from rest. The situation there is that impulse is not going to be the same. It depends upon all kinds of factors, right? Who hits the baseball? Somebody who's a baseball player, a good baseball player, is going to impart more impulse to the ball than I'm going to hit, or that I'm going to impart to it. Somebody who's a good hockey player is going to impart more impulse to the puck than I'm going to impart to it. The impulse is not predetermined. What we want to do here is typically maximize, usually maximize the impulse. How do we do that? Well, there's two ways. If you increase the force, then the impulse goes up. That makes sense, right? You want the ball to go faster and therefore farther, hit it harder. Stronger people hit baseballs farther. That's why Mark McGwire back in the day got, what did he get, 70 home runs? Okay, Sammy Sosa got 72, I think it was, whatever it was, because they're on steroids. They made themselves stronger. They cheated. You make yourself stronger, you can hit the ball farther because you can impart more impulse to the ball by applying a bigger force. But even those guys that cheated and hit all those home runs, broke the home run record that had existed for decades, even those guys had to be good baseball players. You can't just be strong and hit 70 home runs. You have to know how to hit a home run. That's what the other factor is, time. The time of contact between the ball and the bat. It's form, it's technique, it's follow through. When you hit the ball well, the ball is in contact with the bat or the golf club or the hockey stick or whatever it is for more time. As you maximize the time, you also maximize the impulse. So in the first one, force affects time, time affects force. In the second one, force affects impulse, and time affects impulse. Force and time aren't related to each other. They don't affect each other whatsoever, right? I want to finish off impulse now by showing you a graph that you're going to see. A good chance, in fact, that you're going to see this graph on your diploma exam. I can guarantee you're going to see it on your unit test and probably on your next quiz as well, coming up likely Tuesday. When you see a graph that is a force versus time graph, I want you to automatically think three words. Every single time, not those three words, but three other words. When you see this graph, every single time I want you to think area equals impulse. Now, there are times when you see this graph that you're not actually solving for impulse. You might be solving for something else. That's okay. I want you to think those three words. Area equals impulse. Every single time, no matter what you're asked for, no matter what you're given. If you see that graph, area equals impulse. Now, sometimes you've got a line that's above the x-axis. If you do, then that area is going to be a positive value. But sometimes you've got an area that's below the x-axis. If you have an area that's below the x-axis, like this, then that area is going to be a negative value. This would be positive. This would be negative. and you want to find the total area, the total impulse, therefore, you're going to add those areas up. All the positives added to all the negatives to give you the total impulse, the total area. Now, sometimes you've got to go a little bit further. Sometimes you don't just want impulse. Sometimes you want delta V as well. If you do, if you're looking for something beyond impulse, like delta V, you're going to set the impulse that you found by calculating the area equal to m times delta V. It's not a new equation. It's on your data sheet. We've used it lots. Notice I skipped something there in that equation, though. I didn't list F times delta T. You will not in these equations, or sorry, in these graphing questions, use this equation. Even though it's technically valid, it 9 times out of 10 is almost impossible to use when you get a graphing question. So, see this graph, think 3 words, area equals impulse. If the area is above the x-axis, it's positive. If it's below the x-axis, it's negative. And if you've got to go beyond the impulse and find something like delta V, the change in velocity, set the impulse that you found by calculating the area equal to m times delta V. Let's take a look at an example question. Page 462, it says a golfer hits a long drive, sending a 45.9 gram golf ball. Hey, I noticed right away, that's in grams. I'm going to circle it. I'm not even going to look at the rest of the question before I circle it. I might forget later on to circle that. I might forget to convert that to kilograms. The diagram shows an approximation of the net force as a function of time for the collision between the golf club and the ball. We want to know the impulse provided to the ball and the change in velocity, or the velocity of the ball, the moment the club and the ball separate. One more thing I noticed here, times in milliseconds. When I'm doing a calculation, I want to make sure that's going to be in seconds, right? 3 words should come to your mind right now. What are those 3 words? Yep. Good. Area is equal to impulse. Area equals impulse. Let's get the area. Since we're looking for impulse in question A, let's get the area. The impulse is equal to the area, which is equal to, because it's a triangle, 1/2 base times height. 1/2 of the base, notice we're going from 0.1 to 1.1, so the base is going to be 1.0 times 10 to the minus 3, because it's in milliseconds. Got to convert that to seconds, times my height, which is 5,000. Do the math there, works out to be 2.5 Newton seconds, or we could say 2.5 kilograms meters per second. Either one would be okay. That's the impulse provided to the golf ball. Now, if you're a golfer, a good golfer, maybe you could provide more impulse to the golf ball by applying more force, or by keeping your club in contact with the ball for more time. But in this case, there's that much impulse supplied to the ball. Question B says, what's the velocity of the ball at the moment the golf club and ball separate? Well, before we answer that question, I want to ask you something. At what point do the ball and club separate? I'm going to trace this through, and I want you to yell at me. I want you to yell, now, when I reach the point where the ball and club separate. Don't be afraid to yell it. When the ball and club separate, yell at me. I tricked you. I kind of paused there. That's not where the ball and the club separate. That's what a lot of people think, right? Because that's the peak force, right? Think about what's going on here, though. When the club hits the ball, the force increases, and it progressively increases over time, over a very short period of time, about 0.5 milliseconds, but it keeps increasing. Why? Because the ball squishes. The ball squishes actually to a size that's barely half the size of a normal golf ball. If you could get slow motion video of a golf ball sitting on a tee and you're hitting it with a driver, you compress, you squish that golf ball to about half the thickness of its normal thickness. It's amazing how small you actually make that golf ball, how much you actually compress it. You guys know that by Hooke's law, when it compresses, when an elastic compresses or a spring compresses or a golf ball compresses, the force increases, right? F is equal to kx. The force increases as it squishes more. So the force gets bigger and bigger and bigger until a point when it experiences maximum compression. And then the ball can't compress anymore. So what happens then? The ball starts going back out to its equilibrium, to its normal position. What happens then? The force decreases. Well, the ball is still in contact with the club. Think of it this way. At this point, the force is 4,000 newtons and 3,000 newtons and 2,000 newtons. If the club isn't touching the ball, how do you have a force of the club on the ball of 4,000 newtons? Right? The point where the ball and the club separate is when the club is not pushing on the ball, when the force between the club and the ball is 0. So the club and the ball are in contact for the entire graph, which is good because that's the impulse that I just found for the entire graph. Now, let's set that impulse equal to m times delta v. Remember, don't set it equal to f times t. We don't want to use that here. Look at this graph. Tell me why we don't want to use f times delta t. What force do you use? Seriously, the force is changing from 0 to 5,000 back to 0. What force should you use? Well, technically, you could use the average force, but it's more hassle than it's worth. Just don't use it. Use m times delta v. We know the impulse is 2.5. We know the mass is 0.0459 kilograms. You could solve for the change in velocity, delta v. When we do that, divide 2.5 by 0.0459, we get 54.5 meters per second. The change in velocity of the ball was 54.5 meters per second. It was at rest. So if the change is 54.5, then the final velocity will also be 54.5. There's my answer. Let's give you a few minutes to work on the questions on page 462 that go with that. And when you're finished those questions on page 462, I would like you to also work on worksheet number 2 that you've done 5 questions on already. I want you to finish that worksheet. So it's going to be questions 6 to 9. 6 questions, about 15 minutes, and an entire weekend to finish up.